Today we study section 4.2, Rolle's theorem and mean value theorem. Take a review first about the theorem, about the theorems that we have learned so far. The first theorem we learned is the squeeze theorem in section 2.3. Essentially, this theorem says that if two curves approach the same point, then any curve lying between them will approach the same point. Here, the blue curve and the red curve approach the same point. The green curve is a curve between them. Graphically, we can see that the green curve also approach the same point. The second theorem that we learn is the intermediate value theorem in section 2.6. Basically, this theorem says that a continuous curve cannot jump over a horizontal line. Here, we have a continuous curve. If you draw a horizontal line, the horizontal line between the two endpoints, left endpoint and right endpoint, then the horizontal line must intersect the continuous curve at least once. The third theorem is extreme value theorem in section 4.1. It says that a continuous curve over a closed interval must have a highest point and a lowest point. This is a continuous curve. Function value at A is the solid point. Function value at B is the solid point. This curve, because it is continuous, it must have a maximum value and a minimum value. The maximum value is this point, the highest point here. The lowest point is this point. The minimum value occurs at this point. When a curve is continuous and the interval is closed interval, it is guaranteed the curve has a maximum and a minimum. This is an extreme value theorem. This is a review about the theorems that we have learned so far. Now, next, we study two more theorems today, Rolle's theorem and mean value theorem. Let me present the theorems first before I show you examples. If you draw diagrams, it is easy to understand these two theorems. Okay, Rolle's theorem first. Given a function f, if the function satisfies the following three conditions, then we will have this conclusion. Condition 1, function is continuous on the closed interval AB. Yeah, this function is continuous on the closed interval AB. Also, this function is continuous on the interval AB. Condition 2, function value at the two endpoints are equal. The function value at this point A is the solid point. At B is the solid point. These two solid points, they have the same height. A height is function value. So function value at A and B are equal. And also about this curve, the two endpoints, they have the same height. So function value at the two endpoints are equal. Condition 3. Function is differentiable everywhere over this interval. Over the interval means everywhere between A and B. This curve is not differentiable everywhere between A and B because this curve has a corner here. At a corner, the function is not differentiable. So this curve doesn't satisfy condition number 3. How about this curve? This curve is smooth everywhere, no corner. So this curve is differentiable everywhere between A and B, and therefore satisfy condition number 3. The conclusion is there is at least one point between A and B. Their derivative is 0. Their tangent line is horizontal. Yes, about this curve, I can see 2 points where tangent lines are horizontal. How about this one? This one, because this one doesn't satisfy condition number 3. So this theorem, Rolle's theorem, cannot be applied to this curve. This curve, you cannot find tangent line that is horizontal. No tangent line on this curve is horizontal. Essentially, make a summary. Rolle's theorem essentially says that if a curve is continuous and smooth means no corner, and the 2 endpoints have the same height, then at least one tangent line is horizontal. This is calculus language about Rolle's theorem. Here is a geometrical language about Rolle's theorem. The second theorem, mean value theorem. It is similar to Rolle's theorem. Given a function f, if the function satisfies these 2 conditions, then we have this conclusion. Condition 1, function is continuous on a closed interval AB. We have 2 curves here. Both are continuous over the interval AB, continuous. Condition 2, function is differentiable on the open interval. This condition says that function should be differentiable everywhere between A and B. Now, this curve doesn't satisfy condition 2 because there is a corner here. So this curve, this function is not differentiable at a corner, not differentiable everywhere between A and B. How about this curve? Yes, this curve, you see, has no corner. It is smooth everywhere. So this curve satisfies condition number 2. Now, conclusion. Between A and B, you can find a point C such that derivative at point C, derivative is slope of tangent line, is equal to this number. What is this number? What is this number? If you join the 2 endpoints AB with a line, then the slope of this line is y2 minus y1 over x2 minus x1 by slope formula. Point B, coordinates is B, function value at B. point A, the coordinates are A and function value at A. So y2 minus y1, f of B minus f of A over x2 minus x1, B minus A. So this number is the slope of this blue line. This conclusion says that slope of the tangent line is equal to slope of this secant line. So slope two lines, when slopes are equal, the two lines are parallel. So actually, this conclusion says that you can find a tangent line, at least one tangent line, that is parallel to the line AB. This is the conclusion. So the mean value theorem essentially says that if a curve is continuous, condition 1, and is smooth, condition 2, low corner, smooth, then at least one tangent line is parallel to the line AB. Essentially, mean value theorem says this. This is a calculus language about mean value theorem. And here is a geometrical language about mean value theorem. This number is the slope of the line AB. The book also calls this number the average slope of the function over the interval AB. And also, the book also calls it the average rate of change of the function over the interval AB. These two terms, they mean this number. Actually, Rolle's theorem is a special case of mean value theorem. When function value at A is equal to function value at B, then the right side of this equation is 0. Then this equation says that derivative at C is 0. In this case, mean value theorem is the Rolle's theorem. So when f of A is equal to f of B, mean value theorem is reduced to Rolle's theorem. Some examples about Rolle's theorem and the mean value theorem. Example 1. Determine whether Rolle's theorem applies to the following functions on the given intervals. So you need to have a check the three conditions in Rolle's theorem. If Rolle's theorem can be applied, find the points that are guaranteed to exist by the theorem. Consider this function and this interval first. Rolle's theorem has three conditions. Condition 1, the function should be continuous on the given interval. Because this function, it is not a function that is intentionally constructed. Usually, piecewise defined functions are intentionally constructed. This function is not a piecewise defined function. So it is not a function that is intentionally constructed. So the function, because it is not a function intentionally constructed, it should be continuous everywhere on its domain. The domain of a function is the set of the x values where the function values are computable. If you plug in any number in x, you will see that the function is computable. So the domain of the function is any number from negative infinity to positive infinity. So the graph of this function is continuous everywhere. In particular, the function is continuous on the given interval. So condition 1 in Rolle's theorem is satisfied. Now have a check with condition 2. The function value should be equal on the two endpoints of the given interval. I compute function value at left endpoint, -2. Plug in -2 in x, then I get the function value. It is -18. Plug in the right endpoint, 2 in x, then I get function value at 2 is 2. Oh, function value at left endpoint is not equal to function value at the right endpoint. So this function and this interval, they don't satisfy the second condition of Rolle's theorem. Conclusion: Rolle's theorem cannot be applied to this function and this interval. The second function, number 2. This function, again, it is not an intentionally constructed function. It is not a piecewise defined function. So the function is continuous everywhere on its domain. You can try some numbers with your calculator. Say, if you plug in +2 in x, calculator says that computable. If you plug in 0 in x, calculator says that computable. It is 1. If you plug in say -7 in x, then calculator also says that computable. So this function actually is computable for any number. So the domain of the function is -infinity to +infinity. Therefore, the function is continuous everywhere on -infinity to +infinity. In particular, the function is continuous on the given closed interval, -1 to 1. So the first condition of Rolle's theorem is satisfied. Now have a check with the second condition in Rolle's theorem, whether or not function values at the two endpoints are equal. Plug in left endpoint of this interval in x, then we get function value at -1 is 0. I plug in the right endpoint of the interval in x, function value at 1 is 0. So function values at left endpoint is equal to function value at the right endpoint. The second condition of Rolle's theorem is satisfied. Okay, now have a check with the third condition in Rolle's theorem. The third condition in Rolle's theorem says that the function should be differentiable everywhere between -1 and 1. Okay, now let me compute derivative on the function. This is difference rule. And one constant derivative is 0. X to 2/3 power function. So I can apply formula for power function to get 2/3 power. X to power -1. 2/3 -1 is -1/3. Because this guy, the power is negative, I can move it to the denominator. So this is derivative of the function. clearly the derivative doesn't exist when x is 0 because 2 over 0 not commutable. So derivative at 0 doesn't exist. Therefore, the function is not differentiable everywhere between -1 and 1. So Rolle's theorem, the third condition of Rolle's theorem, is not satisfied. Conclusion: Rolle's theorem doesn't apply to this function on this interval. Second example. Second example is about mean value theorem. Given this function here, absolute value of x, and the interval is -1 to 1. There are 3 questions. The first question: determine whether the mean value theorem applies to, there is a typo here, to the function on the given interval. If the answer to this question A is yes, then do the following 2 questions. If the answer to this question is no, then you don't need to do these 2 questions. You don't need to answer these 2 questions. Okay, now let me try to answer this question. Okay, determine whether the mean value theorem applies to this function and this interval. Mean value theorem has 2 conditions. Condition 1, the function should be continuous on the given interval. Second condition, the function should be differentiable everywhere between -1 and 1. Okay, now I plot the graph of this function. It is easy to plot the graph of this function. Yeah, here. This is the graph of this function. I can see that when x is 0, the graph has a corner there. At the corner, low derivative. So derivative of the function at 0 doesn't exist. Therefore, this function is not differentiable on the open interval, -1 and 1. Open interval doesn't contain left endpoint and right endpoint. So differentiable on the open interval, that means that differentiable everywhere between -1 and 1. So this function doesn't satisfy the second condition of mean value theorem. As a result, mean value theorem doesn't apply to this function on the given interval. The third example, given this function and this interval, determine whether the mean value theorem applies to this function on this interval. Second question, if so, find the points that are guaranteed to exist by the mean value theorem. The third question, plot the graph of the function on this interval. Then join the 2 endpoints of the graph with a line. Then on the graph of this function, mark the point P, at which tangent line is parallel to the line that join the 2 endpoints. Okay, let's answer the first question. Determine whether mean value theorem applies to this function. Again, mean value theorem has 2 conditions. The first one is the function should be continuous on the given interval. The second condition is the function should be differentiable everywhere between the two endpoints of the interval. This function is not a piecewise defined function. So this function is not a function that is intentionally constructed. For a function that is not intentionally constructed, its graph must be continuous everywhere on the domain of the function. The domain of this function, you can try some numbers. Say, if you pick positive 3 and plug in positive 3 in x, then calculator says that, computable. If you pick 0 and plug in 0 in x, then you will get 1 over 0, not computable. If you plug in -7, for example, in x, then -7 plus 1 over -7, computable. So the domain of this function is any number except 0. This is the domain. Therefore, the graph of this function is continuous everywhere from -infinity to 0 and from 0 to positive infinity. So continuous everywhere except at 0. In particular, the interval 1 to 3 is contained by the domain. So the function is continuous on this given interval. The first condition of mean value theorem is satisfied. Now, let's have a check with the second condition of mean value theorem, whether or not the function is differentiable between 1 and 3. Okay, now I compute derivative on the function. I can use summation rule. Derivative on x is 1. Derivative on 1 over x, I apply quotient rule, quotient formula. Then I get -1 over x squared. So this is the derivative of the function f. Clearly, the derivative x6 is computable for any number between 1 and 3. Say, if you arbitrarily pick a number, say 1.5, plug in 1.5 in x, computable. So derivative x6 everywhere on this interval. And therefore, the second condition of mean value theorem is satisfied. As a result, the mean value theorem applies to the given function on the given interval. Now, question B. Find the points that are guaranteed to exist by the mean value theorem. That means that you need to solve this equation for C, right? Mean value theorem says that there is a C so that this equation is true. Okay, now the interval AB is 1, 3. So B is 3. So f of 3 minus A is 1, f of 1. So the denominator is 3 minus 1. Okay. Function value at 3. Plug in the number 3 in x. Then again, function value at 3. This is a function value at 1. Derivative of the function is this. Now I plug in C in x to get derivative at C. Solve this equation, then I get a point C, square root of 3. Question C. Make a sketch of the function and a sketch of the line that passes the two endpoints. Okay. From 1 to 3, the red curve is the graph of the function f. The blue line is the line that joins the two endpoints. Then mark the point P at which the slope of the function, the slope of the tangent line to the graph of the function. The slope of the function equals the slope of the secant line. That means that mark the point where the tangent line is parallel to the secant line that join the two endpoints. Okay, now which point? The point P should be here. Yeah, there. Tangent line is parallel to the line that join the two endpoints. And the corresponding x coordinate of this point is the point C, square root of 3. At square root of 3 at this point, tangent line is parallel to the line that join the two endpoints. This point C is guaranteed by the mean value theorem. The last example today. This is the problem number 45 on this page in the book. Use the mean value theorem to explain why if a runner completes a 6.2 miles race in 32 minutes, then he must have been running at exactly 11 miles per hour, at least twice in the race. Assume the runner's speed at the finish line is 0. Let me plot the graph of the position function of the runner. When time is 0, the runner was at the starting point, so his position was 0. When time is 32, he was 6.2 miles away from the starting point, so his position is 6.2. And I assume this red curve is the graph of the position function. Now I apply the mean value theorem to the position function on this time interval. Mean value theorem guarantees between 0 and 32, there is a instant of time c where derivative is equal to the slope of this blue line. This blue line joins the two endpoints of the red curve. This is guaranteed by the mean value theorem. Position at 32 is 6.2. Position at 0 is 0. Then 32 minus 0. Actually, this number is the average velocity of the runner over this time interval. Position 6.2 minus position 0 is the distance traveled by the runner on this time interval. And 32 minus 0 is the time elapsed. So distance traveled over time elapsed, average velocity. The unit is miles per minute. If we translate the unit into miles per hour, then this number is 11.625. Recall that derivative on position function is velocity. So this equation says that at some time c between 0 and 32, the velocity of the runner is this number. Okay, now keep this information in mind and also know that the speed of the runner at the beginning when time is 0, and also by assumption the runner's speed at the finish line is 0. Then I plot this graph of the velocity. When time is 0, velocity is 0. So the graph at 0 is this point. When time is 32, velocity is also 0. So the graph at 32 is this point. Between 0 and 3, there is a C where velocity is this number. I assume the point here is height is 11.625. So the graph of the velocity is at least as height as this point. So the graph of the velocity look like this. Okay, now I can explain the question. Okay, the question is, the runner must have been running at exactly 11 miles per hour at least twice in the race. Suppose 11 is here, lower than this point. Now, through 11, I draw a horizontal line. Then graphically, I can see that the horizontal line intersects the graph of the velocity at least twice, once and the second time. Okay, so the corresponding time, the time here and the time here, at these two instants of time, the velocity of the runner was exactly 11 miles per hour.